So our next speaker is Akash. Dixit on a more conventional, I would say, detector style for particles.
Sure. So my name is Akash. I'm going to be talking about another experiment looking for WIMPs, the Cryogenic Dark Matter Search. So the best way to probably read this title is from bottom to top. So we use detectors to do the Cryogenic Dark Matter Search. And these detectors are made out of germanium, and we keep them really cold. And things happen in these detectors, such as charge transport, and that's what I study. So here we go. So understanding dark matter, I think Derek gave a pretty good introduction of what dark matter is. There are sort of three ways to sort of look at this. The first one is indirect detection, which you talked a lot about. The second is direct detection, which is what we work on. And the third is creation, which I think is the coolest. You try to create these dark matter particles in these accelerators. Specifically, we're looking for WIMPs, and we use these germanium detectors to do that. And I'll be talking about effects that happen in these detectors. But really, it's a lot of words, but the most important thing on this slide is that picture, that there's a lot of dark matter in comparison to the visible matter that we see. And so it's a really important problem that we're trying to understand. Okay, so I'm going to briefly go over this again. Indirect detection here, I just pointed out two methods that are used. The rotation curves, he talked about those. And I just want to say a little bit about the gravitational lensing. I think this is probably the coolest way. The dark matter that's between us and a galaxy cluster or quasar far away is actually warping the space-time around it. And so when light travels towards it, it gets bent around, and then we see it. And I think this is really awesome. So we know that there's something in between us and a galaxy or a quasar really far away. We just can't see it. And we know that because light is being bent. So now WIMPs. These are the particles that we are looking for through direct detection. And like Derek said, of the four fundamental forces in the universe, WIMPs interact through two of them. The first one, gravity, like I talked about, that warps space-time in these massive clusters. And the second one is the weak nuclear force. So when I say weakly interacting massive particles, I don't mean that they interact weakly. What that means is they interact through the weak force. So that's some confusion that I had for a long time as well. Other people have as well. Okay, so this is what we do. So we have these germanium detectors on they're these little hockey puck kind of things. And on the flat surfaces, we have different sort of sensors looking for other different kind of things. So this is sort of the picture of what happens. The WIMP comes in and interacts with the germanium nucleus site. It bounces out, and that interaction causes other things to be emitted, such as electrons or phonons. And so I've put on the top and the bottom what we use to collect these different signals. We use TES arrays to collect the phonon signals, and then we have these conductors on the bottom and on the top to collect the charge, the electrons that are emitted also. So about WIMP detection in general, so there are three sort of things that we can look for in a WIMP interaction. The three being ionization, which are just electrons, phonons, which I guess you could think of as heat packets, and scintillation, which is light, which is what xenon looks for. And so I've put a couple of these experiments here and where they sort of fall on what they look for. And so CDMS, the Cryogenic Dark Matter Search, which is what I work on, sort of falls in the range of ionization and phonon. So we look for these two things from our detectors. A note about, actually no, I'll talk about that later. Okay, so this is probably the most important slide in this presentation, and it sort of gives the motivation for why I do what I do. So when we get these phonon and electron signals, we have to decide what caused this amount of phonons and this amount of electrons to be emitted from the detector. And so we look for these WIMP signatures, these ionization and phonon yields. And the WIMP signature for that is, for every one phonon that you get one electron that goes along with it. And that's sort of indicative of a WIMP interaction. And all the other background interactions that we don't care about sort of look like 3 electrons for every phonon that you get. But like I showed over here a couple slides ago, the collection of the charge occurs on the top and the bottom of this detector. And so what has to happen is, from where the electrons got emitted, they have to travel up or down towards the collection site, and then they have to get collected. But in the meanwhile, while they're traveling through the detector, they get trapped sometimes. And so, one electron gets trapped, 2 electrons get trapped, and all of a sudden, a background particle interaction now looks like a WIMP interaction. And this is a significant problem, and so this is sort of what I work on, the physics of how the electrons move through the detector so we can better characterize why this sort of stuff happens. So this is, I think, a really cool thing to talk about. This is just an overview of how CDMS operates their detectors. So over there on the left, I've put a picture of the germanium detectors themselves. They're 3 inches in diameter and 1 inch thick. And they're these little hockey puck things, like I said. And you can see the grid lines there that represent the phonon array, the TES array that senses for phonons. Then what we do is we stack up these detectors and put them in a tower, and that's connected to a bunch of electronics. And then we take these towers and we put them in these little arrays, and we stick them in this fridge. And this is, I think, the coolest thing ever. We start the fridge at room temperature, which is 300 Kelvin. We're at 300 Kelvin now. Then we put it in a liquid nitrogen bath, which takes it down to 77 Kelvin. Then liquid helium, which takes it down to 4 Kelvin. Now, space by itself is closer to 3 Kelvin. Then we put it in a dilution fridge, which contains helium-3 and helium-4, which takes it down to 0.03 Kelvin. It's 100 times cooler than space, and I think this is the awesomest thing. And like he said, the reason that we do this is that we want to be really sensitive to vibrations from these WIMP interactions, because that's what the phonon signals are. They're just vibrations, heat that gets outputted from a WIMP interaction. And so if our germanium crystals are extremely still, and then we see a vibration or a heat signal, a phonon, we know that it was from an interaction and not from just thermal oscillations of the germanium crystals themselves. So this is sort of, didn't go forward. All right, so this is the experiment setup that I use. So we have this germanium crystal that's this green hockey puck. It's cold. We apply an electric field to it. It can go in either direction. Then we have this laser up at the top. That's that black line. And then we pulse light onto the top of it. And what this does is it generates electrons, and right at the surface of the germanium crystal. Then because of the electric field, these electrons have energy, and they want to drift through the crystal. And so here's a little animation of what happens. So some of the electrons get all the way through towards the other side, where we can collect them and read them out using the electronics that we have. Other electrons get stuck, trapped, or whatever happens in the middle, and that's sort of the problem that I'm trying to study. And this is sort of the basic experiment setup of what I do and how we're able to measure trapping and effects such as that. And so what I work on mostly is the electronics part of it, because that's really important, because we want to be really sensitive to really small signals so that we can tell when something has been trapped. Okay? And this is electronics. It's really messy, but basically what I have is a charge amplifier, and what this does is it takes a really small signal. So here's the basic principle. Electrons moving, charge moving is by definition current. So we have a current moving through this detector, and that's what this amplifier looks for. It amplifies a really small current that's moving through the crystal, and so we can make direct measurements of the current or the electron, the charge transport within the crystal, and then when charges get trapped, we can see a decrease in the current, and so that's how we make direct measurements of the trapping itself. And that's what we use this amplifier for. So this is a cool slide here, because on the top left I have sort of the ideal case where all the charge gets through the detector. And the output on the amplifier would look like I started with electrons and they all move through all at the same rate, so I have a constant current. So that the graphs on the right represent current. And then on the bottom left, this is actually what happens. And what we see there on the right side, I have the data there, you can actually see that it's not a constant current. You get this decay in the current. And that yields a lot of useful information about transport and trapping. And so that's sort of what we look at. So I have the same graph right here again. And so this is sort of what we do after the fact. After the experiment's done, we've collected all this data, then we go in and we fit an exponential on top of this pulse. And so we get, here's an exponential. So that tau that we have there, e to the minus t over tau, we call that the trapping time. And from the trapping time, we can get what's called a trapping length. So distance equals rate times time. That's an equation we all learned in high school. So that trapping time is the time, and then we know the velocity or the rate because we can measure how fast these electrons move through the crystal, because we know how thick it is, how long it took them. So we have a velocity. And from those two things, we can get a length, that lambda equals the trapping time times the drift velocity. And this trapping length is really important because the trapping length is related to the different processes, or the rates of the processes that cause trapping to occur. And so we use lambda, that trapping length. Actually, we use 1 over lambda, which is what my next slide is. So this is a really busy graph. This is sort of what was published in Kyle's thesis. So 1 over lambda is related to, like I was saying, the rates of processes. So there's a couple processes that we think occur within the germanium crystal. I'm not going to get into too much of what they are, actually. And so I plotted this against electric field. And so we see different processes turn on at different points in the electric field. For different regions of the electric field, electrons get trapped for different reasons. And those reasons are indicated by this 1 over lambda factor. And so this is a really nice graph because it sort of with more data we can probably conclusively say that these are the processes that are responsible for charge trapping within the detector. And so that's hopefully future work I get to do. Sort of what I'm working on now and for the future is to get better resolution with the amplifier. And so as you notice, the data was sort of bumpy and ringy, which is a problem always. Electronics is always a problem. And so there was some mismatch termination in the fridge, and so we solved that, and we have sort of smoother curves now. We can get better data using that. Increasing the amplifier bandwidth gives us better understanding of what the pulses look like in the time domain. We get better details. And what we need more is just more time to do this. We need more runs. We need more laser pulses firing on the crystal, more charges being transported through, and just us watching that. And that will give us a better understanding of the physical processes that are governing charge transport. Just want to thank Aaron Phipps, who's a graduate student in the lab, who's helping me on a day-to-day basis, Professor Sadoulet, and the Rosales Foundation. Thank you. Any questions? Yeah.
So you